Hi guys, Mr. Pope from Winter Grammar School for Boys. Just wanted to do a fairly quick video, hopefully quick, I don't want to spend too long, just talking about some very basic principles of forces in mechanics. Okay, so what we're going to be looking at today is looking at essentially introducing the concept of Newtonian mechanics. Okay, now Newtonian mechanics only really apply to objects that are, well, kind of bigger than microscopic, well, nanoscopic, essentially bigger than atomic things, atoms and so on. But really, when we start looking at cosmic scales, what do I mean? I mean like planets and how they interact, that kind of thing. An example of what objects Newtonian mechanics can be applied for is, let's say I've got a ball and I apply an impulse to that ball by kicking it, and I want to calculate how far the ball goes in its flight. Okay, now the ball is an object that's clearly a lot bigger than anything on the atomic scale, but it's also nowhere near as large as something on the cosmic scale. Now, when you're dealing, an example of where it's not okay at the atomic scale is maybe, well, let's say you've got some fundamental particles, and maybe the quarks are interacting in such a way that negates gravity, and we start looking into the realms of gluons and the electromagnetic spectrum. At this point, we would need to use quantum mechanics. Okay, and so Isaac Newton wouldn't have known about that, and he wouldn't have considered it. As far as Isaac Newton, the English guy from the late 1600s, would have thought, is that if there were particles and they were that small, they would have behaved just like marbles or bowling balls or other objects we can hold in our hand. The one thing he did kind of get right, and cosmic things, which we was particularly interested in, elliptical orbits, stuff like that. Well, essentially there's a whole branch of physics to do with that, and it kind of looks at astrophysics. And his laws aren't wrong per se at that level, but they need to be tweaked, or rather taken in a larger sense. And I'll put an asterisk around that, because, well, there's inverse square laws of force fields, gravity being an inverse square, that kind of thing. Essentially, Newtonian mechanics that you can be dealing with at A level is just going to be dealing with regular objects, things that you can deal with your size. The other thing, maybe I should have put size here, is the other thing that Newtonian mechanics really is only applicable for is when the speed. Okay, so really, as long as the speed of the object you're dealing with is either greater than or equal to 0, you can't have negative speed. I mean, you can have a negative velocity, but not negative speed. And really, it needs to be much, much lesser than the speed of light. Okay, and the speed of light is approximately 3 times 10 to the 8 meters per second. Okay, now Newtonian mechanics really only works when you've got objects that are essentially bigger than atomic, smaller than cosmic planets, and the speeds are fairly slow when you compare it to speed of light. So what happens when things are speed of light? Well, you've got you've actually got special relativity, relativity, you're going to have to apply Lorentz transforms on speed, distance, mass. There's going to be all kinds of distortions and dilations depending how fast you go. It's its own special branch, and you can't just apply the rules that we're going to be looking at today. But essentially, for normal-ish size objects, because we're human beings, and speeds which are fairly slow in the grand scheme of things, then Newtonian mechanics has a very, very small percentage error when taking, you know, the rest of these things into account. So they're pretty much as accurate as we can get. Okay, so what's the underlying thing of Newtonian mechanics? Well, for me, Newton's second law of motion is that force, which is a vector, is the rate of change with respect to time of momentum, rho. And rho, by the way, is mass times velocity. Okay, so m is mass, and we usually deal with that in kilograms. That's the SI unit for mass. Velocity, we deal with meters per second, like so. And later on, when you learn about the product rule, essentially force is mass times by the change with respect to t of velocity plus velocity times by the change with respect to time of mass. Okay, now you learn about this, and by the way, velocity is a vector, so I'll underline that, underline that, underline this. So when I underline, I'm talking about vectors. So this is, force is a vector, and it's measured in newtons, or just N, and that's the force. And by the way, a force is just an effect that, if you left it unopposed, will cause a change of motion. It will cause some acceleration. We'll be seeing how that's related in a second. But essentially, classically, this is what Newton would have said. And now, as far as A-level maths is concerned, this d by dt of m is saying how does the mass change with respect to time. And for us, the mass doesn't change of an object. For example, in the ball kicking experiment, when I kick the ball, the mass of the ball stays constant all the way through the flight. You know, the ball doesn't suddenly get heavier or get lighter, it just stays the same. And you're probably thinking, oh, okay, so fine, but when will the mass decrease or increase? That seems a bit weird. Well, it's very simple. Let's suppose you've got a rocket. Here's my rocket. And when it initially fires at t equals 0, it's thrusting out all of the burnt fuel, creating thrust, and at some point it's got a mass of, say, m1. And then, let's say t seconds later, the mass of the rocket has actually gone down. So the mass now is, say, m2, which is less than m1, because there's less fuel. The fuel has been expended. But let's suppose, because the fuel is only interacting with the engine at that point, then there's a constant thrust pushing down. So even though there's less fuel, because it's being burnt at a rate, there's still that same thrust going on t seconds later, but that thrust is going to make more of a difference because the rocket is lighter. Okay, so literally rocket science. When we're dealing with Newton's second law at A level for objects that don't change mass, then it's this part that we only need to consider, because the change in mass with respect to time is 0, which means this whole term disappears. So we're just left with the first. And then finally, what does this all tidy up to in the end? Well, force equals mass, which is a constant in our case, and then dv dt, if you remember from last time, it's the gradient of a velocity time graph that's going to be an acceleration. So for very, very simple Newtonian problems, forces equals mass times acceleration is pretty much going to be your go-to, and you can skip all these previous stages. Essentially, force equals mass times acceleration is the end result that you're looking at here. So let's talk about another key concept, and that's equilibrium. Equilibrium. Now I always get this confused, the spelling of it. I can never remember if it's two I's or otherwise. No, I'm just being silly. So what does equilibrium mean? Well, I want to get this concept down. So what does it does? It does not mean that the object is stationary. And what does that mean? It means its velocity is zero, i.e. it's standing still. Now, what it means actually is that the acceleration is zero. So that means either the velocity is zero because it's just not moving, or the velocity is constant. And one of the main points of Isaac Newton's referential frames is that if you were travelling at a constant velocity, or you were zero, which to be fair, zero is a constant, then you would not be able to tell if you were moving at all. Now, some people might experience this if they're in automobiles, in cars, vans, lorries, that kind of thing. And other than the obvious judder, if you're looking out the window and you're travelling at a constant speed and the car next to you is travelling at a constant speed, then you can't tell which of you is moving. And also you can't really feel any forces on yourself that you're moving either. As far as you're concerned, you're protected from the wind. You aren't experiencing any thrust or resistance while you're in the car. You, as far as you're concerned, you're just moving at a constant velocity. So this is a key point. When it's in equilibrium, essentially if the acceleration is zero, then necessarily the force vectors must equal zero as well. And by the way, this must be the net force, which is interesting. Essentially, that means the consequence is that all the forces going in one direction must equal all the forces going in the opposite direction for every single direction. So that means forces going to the right minus all the forces going to the left, that must equal to zero. Right? Or another way, the magnitude of the forces to the left equal there, so then the net sum must be equal to zero. And this can be in every direction. Essentially, what we're going to be saying is that forces cancel out to zero when a body is in equilibrium, i.e. it's moving at a constant velocity, or it's not moving at all. Okay. Now, there's a couple of key points, just jargon really. Oh, my Hoover, jeez. Hi there, sorry about that. Just had to wait about an hour. Right, okay, so what were we saying? Okay, so we're talking about equilibrium. Well, let's just dive in with an example. Okay, so let's have an example. Oh no, that's not what I was going to do. I was going to define some key points. So, first of all, when we're talking about a particle, okay, and we talk about modelling things as a particle, we take the mass to be acting at a point of essentially area 0. So, for example, let's say I've got a box that's resting on the ground and it's got mass 5 kilograms. So, essentially, if I treated that as a particle, then what would that mean is on the ground I've just got a tiny infinitesimal point where the force of that 5 kilograms is just acting downwards at that point. Okay, I don't have to worry about the weight distribution of the box, whether it's heavier at the top or heavier in that corner and so on. I can just treat that mass acting at a singular point. That's quite useful. There's various other parts, keywords as they come up, and to be honest, when I go through examples I'll probably just be explaining them as I go along. When I'm talking about when things are smooth, they don't have friction. We'll talk about friction at some point. Yeah, I mean, there's so many key words. A lot of them you can just read and pick up, to be quite honest. Okay, so let's imagine a particle. Here it is. And in order for this particle to be in equilibrium, it currently is at the moment, but let's say a force was acting this way and this force was 4 newtons, and let's say a parallel force acting in the opposite direction, which was k newtons, was acting this way. So the question is, for this particle to be in equilibrium, clearly in equilibrium k equals 4. Okay, now what would happen if k was greater than 4? Then the particle would accelerate to the left, wouldn't it? Because the force is to the left, it's a bigger pulling motion to the left than to the right. Whereas if k was less than 4, then that means 4 would be bigger than k, so it would be pulling the particle and it would be accelerating to the right. Okay, but in the case when this particle is in equilibrium, k is clearly equal to 4. Now, let's take a more difficult example, and this is the case where actually we're going to have to use some trigonometry. So let's suppose, for a second example, I've got a point here, and now I've got, let's suppose there is 5 newtons going to the right. Let's suppose there is I don't know, 3 newtons going downwards. So the question is, what would be, so what force would I need to add for this to be in equilibrium? Okay, so just thinking about it, I need a 5 Newton force working that way to counteract the stuff going to the right, and I need a 3 Newton force going upwards to counteract it going down. So in actual fact, the resultant would be popping out like this. I would only need to add one force that would do, you know, the same as the other two combined. And let's say this resultant force, this R, this is the resultant force. And what properties do I need about that? Well, in actual fact, we can treat it as a vector, right? We've talked about vectors before. I just need to consider the vector. That is 5 newtons left and 3 newtons up. And the angle it makes with the horizontal is this theta. So the magnitude of R is just going to be 3 squared plus 5 squared square rooted. So it's 9 plus 25, so it's root 34 newtons. And the angle it makes, R, the angle it makes, or let's just call it theta, is going to be inverse tan of opposite 3 over 5. And the angle it's going to make with the menu, nope, setup, angles in degrees, so menu, right, okay, so inverse tan, oops daisy, inverse tan of opposite over adjacent. So apparently that needs to be 30.96 degrees to 2 decimal places, or the inverse tan of 3/5 degrees if we're working in degrees. Yeah, so in actual fact, finding resultants is fairly easy. You just have to consider what's going on in all of the directions. Yeah, I mean, I can do a couple of more. I'll do one more. Let's suppose, right, let's take a more wackier example. Let's suppose I have another particle, and this time with respect to an x-axis like this and a y-axis like this, then I have a force acting like this of length 5 newtons, where this angle here is 30 degrees. I have a force acting like this, which is 8 newtons, and this angle here is 60 degrees. The question would be, this is example 3, the question would be, where would the resultant be? Okay, and the orientation of the resultants. Okay, so, well, we can work backwards. We can say there must be an equal and opposite 5 newtons going this way, and there must be an equal and opposite 8 newtons going this way, and we can tell that this is 60 degrees and this is 30 degrees. So what would the resultant of that be? Well, we can slide one onto the other. So I'm going to take this 8 newtons and I'm going to slide it onto the end like so. And the resultant would be a vector looking like that. So just as a rough sketch, the resultant would be looking like this. Okay. Next up, let's suppose they are at wonky angles and you don't particularly feel confident in using Pythagoras or some inverse trig stuff. Then what you need to do is you need to consider finding the horizontal and vertical components of these two vectors. So if you look at the 5 newtons like this, then if we resolve horizontally, so all the stuff to the left will equal all the stuff to the right, then what's all the stuff to the left? Well, if we call this angle theta and we call this r, then clearly this horizontal component of r is r cosine of theta, because cosine of theta is the adjacent part, or the horizontal component over the hypotenuse, and if we times by r both sides we get r cos theta. And by similar reasoning, the vertical component is r sine theta. So all the stuff going to the left, which is r cosine theta, that must equal all the forces going to the right, which by similar logic is going to be 5 cosine 30 degrees plus 8 cosine 60 degrees. Similarly, if I resolve vertically up and down, so all the up stuff equals all the down stuff, then the vectors that are acting vertically are, well, This time it's not so easy. We've got r sine theta plus the other vector force going upwards, which is going to be 5 sine of 30. And this must equal the only force going downwards, which is 8 sine of 60. Okay. Now, there's multiple ways of doing this. Essentially, we've got one equation here, two equations there. And first of all, if I minus the 5 sine 30 from both sides here, so I take this out, put it over to here maybe, move this, hold on, delete this, move this over, subtract 5 sine 30 from both sides, we now have a pair of simultaneous equations for r and theta to solve. And in actual fact, when you think about it, equation 1, r cosine theta will become 5 cosine theta, or so 5 cosine 30, and cosine 30 I believe is root 3 over 2, so this will be 5 root 3 over 2 plus 8 cosine 60, which is a half, so that will become plus 4. And r sine of theta will equal 8 sine of 60, which is 8 lots of 3 over 2, 8 lots of root 3 over 2, which is actually 4 root 3, minus sine of 30, which is going to be minus 5 over 2. So in actual fact, once we've got these two, this is a fairly easy set of simultaneous equations to solve. Well, the first thing we can do is find the angle. Okay, and that'd be fair. Well, that's fairly easy, because if we do r sine theta divided by r cosine of theta, the r's will cancel, and sine divided by cosine is tan of theta. Why is that the case? Because sine of theta is the opposite over hypotenuse, and cosine of theta is the adjacent over hypotenuse, and tan of theta is the opposite over adjacent. And look what happens if I do sine divided by cos. I'll have O over H divided by A over H. And if I times by H top and bottom, the H's cancel and we're left with O over A. Okay, now that we've got tan theta, well, the r sine theta was this one, so it's going to be 4 root 3 minus 5 over 2, all over, and then the cos theta is 5 root 3 plus 4. 5 root 3 over 2 plus 4. So in actual fact, this is going to lead to theta is the inverse tan of that lot, and that's something we can easily do. That will be fraction 4 shift root 3 minus fraction 5 over 2 on the bottom, fraction 5 root 3 over 2 plus 4, and this will give approximately 27.99 degrees, which is pretty close to 28 degrees. So already I know that theta is 27.99 degrees. Now to work out the r value, that's pretty dicey, but there's also multiple ways you can do this as well. And this is what I'm going to suggest. Suppose that this thing equals A, and let's suppose this thing equals B. Then what does that actually mean? Well, this is an advanced bit of trigonometry. R cos theta equals A. So that means cosine theta equals A over R. And if R sine theta equals B, that means sine theta equals B over R. So that means if this is theta over here, we're dealing with a triangle where sine theta is B over R and cosine theta is A over the same hypotenuse R. And now we've got something quite nice. That is, from Pythagoras, a squared plus b squared is r squared. Now this is great, because now that just means r is going to be the square root of a squared, which is 5 root 3 over 2 plus 4 squared, plus b squared, which is 4 root 3 minus 5 over 2 squared. And you can give the exact value if you want to, but for purposes of saving time and to 2 decimal places of what I've done already, I'm just going to leave it to 2 decimal places. So 5 root 3 over 2 plus 4, close brackets, squared, plus brackets 4 shift square root 3 minus 5 over 2, close brackets, squared. So R is just root 89, and that is just going to be 9.433 newtons. 9.433 newtons. Okay, there's various ways you could, to be honest, there's various ways you could have solved this. I mean, later on, we'll be looking, essentially it's how good is your trigonometry at being able to solve these kind of things. This was quite a difficult example, in all fairness, and to solve trigonometric simultaneous equations, generally speaking, to find the angle, you divide one equation by the other, so you've got tan of theta, and you want the sine 1 divided by cos, because you want to abuse that sine over cos is tan, and then to get the length, well, you just consider a right-angled triangle and make R the hypotenuse, and then use Pythagoras. Your calculator actually has an inbuilt simultaneous equation solver, should you wish to use it. That's the Casio FX991EX or the Casio FX CG50. But essentially, this is the main bits I wanted to talk about today. So, yeah, Newtonian mechanics, only really useful for objects that are of relative size to us and speed much slower than the speed of light. Newton's second law of motion is the force vector equals mass times acceleration vector, and equilibrium is when the net forces are 0 and the acceleration is 0. And that doesn't necessarily mean when the object is at rest. Particles are when we treat the object as a point, i.e. their mass acts at a singular point. And yeah, just the forces always have to balance out. It's generally a case of, well, let's tidy this up. So this is example 1. This is example 2. And example 3 is this thing down here. Yeah. So that's it. I've only left 6 questions. Just work through it. And yeah, have fun.